Here is a analysis of data involving the measurements of circumference and the diameter of round objects to determine pi experimentally. So here's a collection of data where using circular objects that range in diameters from about 1 3/4 of an inch to about 15 3/4 of an inch, you measure the circumference and diameter to the nearest millimeter with a variety of methods. Sometimes we wrap the objects with a string, or we can roll them one time, and that'll give you the circumference. But anyway, so these are some relatively good measurements. Now, the first thing you notice is that we have column headers, the diameter, and then the variable d and the units millimeter. So that's in a proper format. But what I'd also like to do is choose this row, and I'm going to convert that to Times New Roman. And in that manner, I can italicize the variables so that they're in the format of what you would see in a book. Let's say italicized variables. There we go. And units are not italicized. Now, the next thing you might notice is that the data is not in any sort of order. Let's put this in an ascending order. So I'm going to highlight this and choose sort and filter and go sort smallest to largest. There we go. Now we have the smallest object first and the largest object last. Okay, so the first thing we need to do is calculate pi. So I'm going to write pi p equals c over d. Now I'm going to take this and I'm going to convert the p to a symbol. And I'm going to italicize everything. There we go. Now we can calculate it. So we say equals circumference, that's B4, divided by A4, and tab out. There we go. Now let's notice that the cross turns into a skinnier version of a cross, and then pull it down, and that calculates all of them. See, that's B4 over A4, B5 over A5, so on and so forth. So there are your experimentally determined values of pi for all the round objects. Now, the next thing we need to do is let's put this in a format that's more reasonable when we also consider the significant digits. Notice that we have in this, for this object here, we have 2 significant digits. So this should be 3.2. We'll round it off. Okay, this has 2 significant digits, the 51. So that's 3.2. Rounding that one off. Okay, we still have 2 significant digits, 3.1, 3.2, 3.1. Okay, we still just have 2 significant digits because you cannot improve the precision of a result from a calculation. So the lowest number of significant digits is the diameter. It's 2. So this one's 3.2. Now we have 3 significant digits. See the 157? So we can say 3.11. And here we have 3.11. And here we have 3.14. There we go. Now, let me fix these up. So we don't want to italicize it, and we want Calibri font, let's say. I'm going to put those in the center. Let's make all these the same font. So I'm going to choose Calibri. You can choose anything and center justify. Okay, now that will be, these are your experimentally determined values of pi to the proper precision. Okay, so we copy that and I'll include it here. Now, the next thing we could do is calculate a percent error based on all the measurements. Okay, so percent error. Okay, so how do you do that? Now I like to include, I don't like to use the absolute value because if the percent error is negative, that means that your result is smaller than the expected value. And if it's positive, that means that your result is larger than the expected value. So we just say equals, open up parenthesis, this your value. Actually, I'm just going to go on and use the values with more precision over here, minus pi. Now, pi in Excel syntax is pi open close parenthesis. And that'll keep pi to many digits. Okay, then we need to divide by pi because we're doing the percent error, and then multiply by 100 to convert it to a percent. There we go. Okay, now we pull that down And then we need the proper number of digits. I'm not going to do that. I'm just going to use 3 for all of them. But we really shouldn't. I'll show you. Let's see, number 2 decimal places. Okay, now really this would only have 1 decimal place. Okay, because you only have 2 sig figs here. So, but I'm going to leave it like that because it's okay. It's not that big of a deal. Okay, now, so there you go. Now, the next thing, now how we're going to do a more in-depth formal analysis, but let me show you another method. This method that I'm about to show you is not really correct, but it's not bad in a lot of experiments, and then I'll explain in another video a more in-depth error analysis involving propagated uncertainties why this does not work, why you should not in general average table values. So let's do this. I'm going to put pi average, okay, and then I'm going to change this to a symbol, and then I'm going to subscript the average, just showing you different things you can do with Excel. And then we will move this over to the right and italicize it. There we go. Now, how do you average data? So we go equals average, right? And open up parentheses, and then choose the population that you wish to average. Okay, there we go. So the average is 3.1, about 3.15. Now let's do a standard deviation. Now we really should, for this many values, we should use the standard deviation of the population. Okay. Now we're going to choose the same population. Do not include the average when you do this. Okay. Whoops, I forgot to put equals. Whoops, and that's the wrong. Matter of fact, let me go back. This should be S pi. Watch what I do here. I'm going to call this. This is sigma. We usually use the sigma for standard deviation. So symbol, and then we're going to subscript that because it's the standard deviation of pi, right? So that should also be. I should have symboled both of them. There we go. Now I'm going to make that a subscript, and I'm going to italicize it and write justify. There we go. Now, to get the standard deviation of this population, you just type STDEVP, standard deviation of the population, and then open up your parentheses, and then choose the population. See that? Boom. Now, that gets the standard deviation. Now, let's see, Calibri 10. Okay, now, if you do that, now this is not really correct, and I'm going to explain why it's not correct. But if we do that, then we have a pi table like this. I'm going to go down here and copy it. So pi table, this is like table values. I'll put tabular. Pi tabular. Now, what you would do is notice that according to our standard deviation of this population, we have an uncertainty of 0.04. Now, that is not a leading one, so since it's not, we're just going to use one significant digit, and we're going to treat that standard deviation as the error in this data set. So notice that that's in the hundredth spot, so I need to round pi off to 3.15. So I'm going to say 3.15 plus or minus 0.04. And that is your experimental value based on this technique, which is actually not correct, but it's okay. I mean, it serves a purpose for what we're doing next. Okay, now notice that we have ourselves a tabular result based on averaging, which once again, it's not technically correct, but it'll serve a purpose for our next discussion to show why it's not correct. But anyway, one thing that's good about this, it does sort of, if you do this with any data set, it does give you an idea of how many decimal places you should report. Like a lot of times when students do a lab, they might report something like pi is 3.1488851, say that. Well, that's all these digits out here are superfluous. They're meaningless. And technically, you really only need 2 significant digits for all these. See that? All that set right there, because we only had 2 significant digits in our measurement when we were talking about millimeters here. So basically, that is reasonable. Now, in the next video, I'm going to do a formally propagated error based on uncertainties in measurements, and that'll give you a better idea why this really technically is not correct. Sometimes it's nice to do anyway, as long as you understand its range of application. Okay, so now one thing I might say, if you do something like this, you might say, hey, that agrees with pi because we have 3.15 plus or minus 0.04. So we would have a range, let's say, of 3.11 to, that's the lower bound, and the upper bound would be what? 3.19, and pi falls in that range, so you would say it agrees. But the problem with that is technically you shouldn't just average data blindly, because as we're going to see in the next video, these really, if you're going to average them, they should be a weighted average. And what we're going to find out is the larger objects are more trustworthy. They would have a larger weight associated with them due to the relative errors when we made our measurements. Okay, so we could definitely say this would be an agreement. Now, another thing about this that you might have noticed is if you do a really bad job and you have one of these values is really bad, then you're going to have a value that's far away from the average for that particular object, and that'll make your standard deviation larger. And then it's sort of like you get rewarded, in a sense, for having this large standard deviation and say, well, it's in agreement with pi, but it's because of a sloppy measurement. So basically, that's what I'm trying to get to here, is that this is really not technically the correct way to do things. These values are okay. The way we did it here, we just rounded off according to the precision of the measurements, the lowest significant digits in the measurements. These are okay. So so in the next video, I'm going to talk about propagated error. But anyway, there's a tabular analysis of data for the experiment involving a determination of pi.